What's up? What's up? What's up? What's up? Can't wear headphones today, man. It's literally breathtaking. I don't wanna wear those headphones. I don't wanna wear these headphones. I'm audible now. Or is it less? Check, 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 check. I'm audible now. Or is it less? Check, 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 check. Okay, so we'll start. I hope everything is fine. But before that, I have to wear earphones. Cause I can't, man. I can't. I literally can't. Okay, so we'll start. I hope everything is fine. But before that, I have to wear earphones. Cause I can't, man. I can't. Now I can. I don't know what the fuck am I doing. Now I can. Yeah, this is better, right? This is way better. Give me a minute, I will post this on Instagram so that people know that I'm back with live streams and I am back today. Took this screenshot, take this here, copy that link, uh, then I come here to my. Yep, I'm all set, ready to go, ready to kill it. Do we have anyone joining with us today? Is there anyone? Is there any beautiful person joining us today? Is there anyone? Dim. There's no one. Anyways, we'll start working, man. Cause working for life is working for working is always better, and we keep working. Cause working is talking. Machine Learning Crash Course by Google. Then what do we do? Then we open this beautiful website. Uh, Start crash course. Pew 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 pew. कोई तो आ जाओ भाई. 8 billion people in this world and there's only me watching my stream. How's it even fair? That is very unfair. Today I'm gonna start with categorical data, by the way. Categorical data. Vocabulary and one hot coding. Okay. The term dimension is a synonym for number of elements in a feature vector. I know this. Is a synonym for number of elements in a feature vector. Feature vector is nothing else but just an array. Okay. There are types of dimensions in an array, which is 1D array, 2D array, 3D array. Okay. Now, how many elements I have that determines the dimension. Some categorical features are low dimensional. For example, snow today. True, false. Okay. When a categorical feature has a low number of possible categories, you encode it as a vocabulary. So when I have a categorical feature which has like a low number of possibilities, okay, possible outcomes, either like rice, rice example. I know you guys wonder why I am always milking the rice example, but listen to me. In rice, what we were doing, classifying it as the Osmansic and Cameo. Okay, so there are two possible outcomes, two possible categories. You put those both in vocabulary. You encode it as a vocabulary instead of one hot encoding. With a vocabulary encoding, the model treats each possible category value as a separate feature. Okay. During training, the model learns different weights for each category. For example, suppose you are creating a model to predict a car's price based in part on a categorical feature named car color. Perhaps red cars are worth more than green cars. Since manufacturers offer a limited number of exterior colors, car color is a low dimensional categorical feature. Okay. Machine learning models can only manipulate floating point numbers. You can't manipulate strings. You can't do anything with strings. You have to show them numbers. Okay. Therefore, you must convert these features into numbers. Since red is given as 0, orange is given as 1, and blue is given as 2. That's how. Now we need to go further. If we just leave it here, okay, after just converting them to index numbers, the model will think that the color black is 5 times more worth than orange, because 1 into 5 is 5, so it will think black is more superior to orange, but it's not, right? We are not seeing multiples right now, we are seeing types of colors. So then the topic comes is one hot encoding. Vocabulary was for low dimensional feature vectors. One hot encoding is for high dimensional vectors. Okay. The next step in building a vocabulary is to convert each index to its one hot encoding. The next step in a vocabulary, after you convert each number to an index number, we convert it to an one hot encoding. What's one hot encoding? Each category is represented by an array of n elements, where n is the number of categories. Okay. Yeah, as you can see the table, it's clearly understandable. Each category you represent as an array of n elements. Okay, let's say car color. Car color has 8 possibilities. So each feature, that is red has 8 elements, orange has 8 elements, yellow blue has 8 elements, blue has 8 elements. Now red will have 1 on red and 0 on all, like that. Okay, it will have diagonally 1 1 1 1 1 1. That's the point. It is the one hot pointer, not the string or the index number, that gets passed to the feature vector. The model learns a separate weight for each element of the feature vector. The following illustration suggests the various transformation of the vocabulary representation. Categories. We have categories as yellow, orange, blue, till blue. Why blue again? I don't know. We to do the index lookup here. After this index lookup, each color has an ID. After that IDs, we pass it to one hot encoding. One hot encoding converts it into a feature vector. Sparse representation. A feature whose values are predominantly 0 is termed as sparse feature. You guys might have learned in your first sem or second sem, which was sparse matrix. Similarly, we have a sparse feature, which is the values are predominantly 0. Like by default, they are 0. When you update it, it becomes 1 or some other value. That's how it is. Many categorical features such as car color tend to be sparse features. Sparse representations mean storing the position of the one in a sparse vector. For example, the one hot vector for blue is okay. Notice that the sparse representation consumes far less memory than the 8 element one hot vector. Since the 1 is the position at 2, the sparse representation for the preceding one hot vector is 2. Okay, the sparse representation consumes far less memory than the 8 element one hot vector. Importantly, the model must train on the one hot vector, not the sparse representation, because sparse representation will also make the model to learn the example I gave before, which is phi is at black is at index phi and orange is at index 1. So if we put it directly into the model through the sparse representation, the model will think that black is 5 times greater than 5 times better than orange. Okay, we don't need that. We need to be each feature to be treated on their categorical weight. Okay, outliers in categorical data. Okay, like numerical data, categorical data can also contain outliers. Suppose car color contains not only the popular color but also some rarely used outliers colors as a mauve or avocado. We saw 8 possible colors. What if there was outliers in that? Outliers in means you don't predict that colors. Rather than giving each of these outliers colors a separate category, you can jump them into a single catch-all category called out of vocabulary. You keep all of the points in a vocabulary and one hot encoding, and you convert them to feature vector. And now when you have outliers, instead of you converting them to another separate array for each of them, you put all of them in one category, which is outliers category, named catch all category, called out of vocabulary. In other words, all the outlier colors are binned into a single outlier bucket. All the outlier colors are binned into a single outlier bucket. The system learns a single weight for that outlier bucket. Some categorical features have a high number of dimensions, such as those in the following table. Words in English, there are so many of them. US postal codes, there are so many of them. Last names in Germany, there are so many of them. When the number of categories is high, the one hot encoding is usually a bad choice. Embeddings, embeddings detailed in a separate embeddings module are usually a much better choice. Embeddings substantially reduce the number of dimensions, which benefits the model in two important ways. When there are high number of dimensions in a data set, let's say words in English, okay, so many words in English. Now, if I had to train the model on that, I wouldn't use one hot encoding because it's usually a bad choice. Because for every word you would make a separate array, would it sound right? Embeddings, you would use embeddings because embeddings will reduce the number of dimensions, which benefits the models in two important ways. The model typically trains faster. Since less it reduces the dimensions, the model trains faster. The model has lower latency. That's the two. Okay. Now coming to the next point, we have hashing. Why is this working? Okay. Hashing, also called the hashing trick, is a less common way to reduce the number of dimensions. Okay. In brief, hashing maps a category, for examples, to a small integer number of the bucket that will hold that category. Set the number of bins in the vector of categories to n, okay, where n is the less than the total number of remaining categories. As an arbitrary example, say n is equal to 100. Choose a hash function. Pass each category to the hash function, generating a hash value. Assign each bin an index number of the output hash value modulo n. A machine learning model can train directly on raw string values without converting these values to numerical vectors. That's very, very, very false. Coming to the next, common issues with categorical data. What are the common issues in categorical data? Numerical data is often recorded by scientific instruments or automated instruments. That's true. Categorical data, on the other often is categorized by humans or by ML models who decide on categories and label, and how they make those decisions affects the reliability and usefulness of that particular data. Now, what they told is we have numerical data and categorical data, right? Numerical data, you make the calculations using instruments. Okay, how loud, the more the surface area, the more loud the music is, like in that way. Okay, there you use instruments, there human doesn't come, there ML models don't come. Similarly, in categorical data, there are no instruments which you could use, but there are human beings who categorize them to check if an animal is a dog or a dog or a cat. You need human beings for that. Okay, you look on some specific characteristics, and then you decide if it's a dog or a cat. Human raters. Data manually labeled by human being is often referred to as gold labels, and is often considered more desirable than machine labeled data for training models due to relatively better data quality. You never know why, because I think humans are genuinely better than uh, better than machine. Uh, Data manually labeled by human beings is often referred to as gold labels. We understood that. This doesn't necessarily mean that any sort of human labeled data is of high quality. There are human errors. Sometimes uh, we misinterpret things. Bias. One second. Okay, coming back. There are sometimes human errors, labels, biases, and etc. Any two human beings may label the same example differently. That's true. Every other human being has different opinions. The difference between human writers' decision is called inter-rater agreement. Okay. Hello, Michael Amanidev. How do you do? One second. Give me 1 second. Just give me 1 second. Next. Coming next point. Any two human beings may label the same example differently. Machine labeled data, where categories are determined by one or more classification models, is often referred to as silver labels. Okay, if humans label it, it's called gold labels. If machines, if ML models label it, it's called silver labels. Not ML models, I guess. Must be an okay. Machine labeled data can vary widely in quality. Check it not only for accuracy and biases, but also for violations of common sense, reality, and intention. True. For example, if a computer vision model mislabels a photo of a chihuahua as a muffin or a photo of a muffin as chihuahua, models trained on that label data will be of lower quality. Similarly, a sentiment analyzer that scores neural words or minus 2.0.25, a sentiment analyzer is when I am talking right now. It tells me if my emotion is negative, neutral, or positive. That's a sentiment analyzer. Okay. Now I'm talking neutral. Instead of it classifying as neutral, it classifies as minus 0.25, which is negative, might be scoring all words with an additional negative bias that is not actually present in the data. An oversensitive toxicity detector may falsely flag many neutral statements as toxic. Try to get a sense of the quality and biases of the machine labels and annotations in your data before training it. High dimensionality. Categorical data tends to produce high dimensional feature vectors. That is feature vectors having a large number of elements. High dimensionality increases training costs and makes training more difficult. That's why we have embedding and hashing. For these reasons, ML experts often seek ways to reduce the number of dimensions prior to training. For natural language data, the main method of reducing dimensionality is to convert feature vectors to embedding vectors. This is discussed in the embedding modules in the later this course. I'm very excited to learn embedding, so much, so much, so much, so much, so much exciting. Feature crosses are created by crossing, taking the Cartesian products of two or more categorical or bucketed features of the data set. Okay, if I have two features and I make a cross product of that, that is feature crosses. Like polynomial transforms, feature crosses allow linear models to handle non-linearities. Feature crosses also encode interactions between features. For example, consider a leaf data set with the categorical features, edges containing values, smooth, toothed, and lobed, arrangement containing values opposite and alternate. Okay, assume the order above in the order of the feature contain columns in one hot representation, so that the leaf with smooth edges and opposite arrangement is represented as 1 0 0 and 1 comma 0. The feature cross or Cartesian products of these two features would be smooth opposite, smooth alternate, tooth opposite, Henji. Okay, 1 to 1, which is smooth opposite. 1 into 0 is smooth alternate, and 0 into 1 is tooth opposite, and 0 into 0 is tooth alternate. Okay, okay, understood, understood. I understood. For example, if a leaf has a lobed edge and an alternate arrangement, the feature curve will have 1 for lobed alternate and value of 0 for all other terms. As simple as that. As if I had leaves feature crosses. Domain knowledge can suggest a useful combination of features to cross. Without the domain knowledge, it can be difficult to determine effective feature crosses or polynomial transforms by hand. If it's often possible, if computationally expensive, to use neural networks to automatically find and apply useful feature combinations during training. Be careful. Crossing two past features produce an even sparser new feature than the two original feature. For example, if feature A is a 100 element sparse feature and feature B is a 200 element sparse feature, a feature cross of A and B yields a 20,000 element sparse feature. Oing, 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 oing. Done with the feature cross. Coming to the feature cross exercises. Okay, what is feature cross exercises? That lets you. I know what a playground is. Don't teach me what a playground is, boy. For this example, focus on the following parts of the playground user interface. Underneath features, notice the three potential model features, which is x1, x2, and x1, x2. Underneath output, you will see underneath features. Okay, you will see a square containing orange and blue dots. Imagine that you're looking at the square forest. Mark the position of sick trees, and blue dots mark the position of healthy trees. Okay, so these are the sick trees and these are the healthy trees. Okay, the blue ones are the healthy trees and the orange ones are the sick trees. Between features and output, which feature? This one is features. Between features and output, if you look very closely, you'll see three faint dashed lines connecting feature to the output. Okay, the width of each dashed line symbolizes the weight currently associated with each feature. These lines are very faint because the starting weight for each feature is initialized to 0. As the weight grows or shrinks, so the thickness of these lines. The dash lies from increases from 0 to 1, and orange blue background now appears. The orange background is the model's guesses as where the sick trees are. The blue background is the model's guesses at where the healthy trees are. The model is doing a terrible job. About half of the model's guesses are wrong because the weight of 1 for x1 and 0 for other features. The model value exactly 6 and healthy. The solution appears just below the playground. Okay. Let me do, I guess, point 0.5. Okay, let me do 0.5. Hey, come on. Point 0.5 here. Okay, almost there. Abe, ma. Let's fucking go, man. Let me make 9.9 or something. Abe, let me click. Array. Let it be 0.5 and 0.5, man. Who cares? Acha. A more sophisticated feature cross. For the second exercise, look at any arrangement of orange dots and blue dots in the output model. Notice the following. The dots from roughly spherical patterns. Boring, man. Who cares about this? Fuck off. Mhm. Ouch. Push me da. Starting again. I'm scared to skip this. What if it's actually important? Let's see, man. I will read it. Then with exercise 1, then let's do. For the second exercise, look at the arrangement of orange dots. Okay. Let me show you the orange dot. These are the orange dots. Orange dots means the sick trees, okay? And the blue dots mean healthy trees in the output model. Notice in the followings, the dots from roughly spherical patterns. The arrangement of dots is noisy. For example, notice the occasional blue dots in the outer sphere of the orange dots. Explore the pyramid area by following. Oh my god, 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 oh my god. Oh my god, oh my god, oh my god, oh my god. Why is it dancing, man? Okay. Pause button, which is a white triangle inside. I know that. After the system has trained at least 300 epochs, press that. Okay. Look at the model. Is the model making good prediction? In other words, are the blue dots generally surrounded by blue? I guess so. Are the orange dots generally surrounded by the orange background? Nah. Examine the value of test loss, which appears just below the output. If this value is closer to 1 or closer to 0, test loss is 0.851. Oh my god. It's not reducing shit, man. Select or deselect by any of. Damn. Damn. Did you see what I just did, man? How am I so smart, dude? Nah, 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 nah. I just did something, man. See? Less than 2. How do I make it less than 2? Hey? I don't know, man. Adjust the learning rate. Zero point 0.3. Let me try again. No. 0.001. 0.01. हो तो गया. It's 0.173. I did that, man. Oh. Oh. This is beautiful. Nice work, man. Which of the following are examples of categorical data? Number of pages in a book, that's numerical. Telephone number could be categorical. Types of French fries. Ooh. So telephone number could be an categorical data. Star rating could also be. Type of French fries is also an categorical data, man. I don't think number of pages in a book is. Machine labels are generally considered more desirable than labels provided by human writers. No, false. Which you are training a model on training a DC data on a training data set that includes that uh, feature color, feature eye color, which can be one of the following six values: amber, blue, green, hue. Which of the following are valid encodings for an eye color value of blue? I guess it's 010000. Which of the following scenarios would it make sense to apply feature hashing? You're performing a feature cross of the following two categorical features. So we have 1, 2, 3, 4, and we have 2. 4 cross 2. How many elements? Cartesian product. Is it 4C2? The 4 comes 1 4 times. 4C2 is like 4 factorial by 2 factorial by 2 factorial, which is 1. Eh? Now, 4 of them come once with the first element of the 2, and 4 of them come with the second element of the 2. So which is 8. 4 into 2 is 8. The answers are very wrong, man. Not gonna lie. Gee. I knew this was. I knew. I'll reattempt this. 0, 1 was not the true answer, I know. My bad. And this was this. And this was 8. And this was telephone number. And this was false. And we are good to go. Submit answers. That's 5 out of 5. Thank you. Eh? Coming back. We have this much to read, which is datasets. I guess it should be easy to cover this today. It should be easy to cover this today. And probably I will start tomorrow with neural networks and all. Pow, pow, pow. बेबो मैं बेबो दिल मेरा ले लो कहाँ से आई जी बेबो बेबो मैं बेबो दिल मेरा ले लो कहाँ से आई बेबो से मेबो बेबो मैं Give me 1 minute, I will be back. Let me drink water and join again. Let me drink water. I'm back, I'm back, I'm back. I am back. The model begins with a leading question. Choose one of the following answers. Okay? If you had to prioritize improving one of the following areas in your machine learning project, which would have the most impact? Improving the quality of a dataset, man. If your dataset is bad, nothing can do. And here's a more leading question. In your machine learning project, how much time do you typically spend on data preparation and transformation? More than half of the project time. Exactly. A dataset is a collection of examples. The definition is very simple. A dataset is a collection of examples. Many datasets are stored in tables, for example, a comma separated values, or directly from spreadsheets or database tables. Tables are an initiative input format for machine learning models. You can imagine each row of the table as an example and each column as a potential feature or label. That's it. Dataset may also be derived from other formats, including log files and protocol buffers. Regardless of the format, your ML model is only as good as the data it trains on. This section examines key data characteristics. There are types of data. We studied like numerical data and categorical data very deeply. Now the another is human language. Okay, how do we talk? The way we talk, etc. etc. Now multimedia is images, videos, and audio files. Okay, output from other ML systems and embedding vectors which are covered in a data unit. Coming to the quantity of a data, the as a rough rule of thumb, your model should train on at least an order of magnitude more examples than trainable parameters. Models trained on large datasets with a few features generally outperform models on small datasets with lots of features. Google has historically had great success training simple models on large datasets. Different datasets for different machine learning programs may require widely different amounts of examples to build a useful model. For example, for some relatively simple problems, a few dozen examples might be sufficient. For other problems, a trillion problems might not be sufficient. What the fuck is happening? Bro, what the hell? Abe, why the hell are you talking, man? Quality and reliability of data. Everyone prefers high quality to low quality, but quality is such a vague concept that it could be defined many different ways. This course defines quality pragmatically. A high quality dataset helps your model accomplish its goal. Okay? A low quality dataset inhibits your model from accomplishing its goal. As simple as that. Is also reliability refers to the degree to which you can trust your data. Bro, this mother. A person forgot to enter value for a house age. Duplicate example. Bad feature values, bad labels, bad sections of our data. Complete versus incomplete examples. I know that. Don't train a model on incomplete examples. Instead, fix or eliminate incomplete examples by doing one of the following: delete incomplete examples, impute well reasoned guesses. As simple as that. Okay. If the dataset contains enough complete examples to train a useful model, then consider deleting the incomplete examples. Similarly, if only one feature is missing a significant amount of data, and that one feature probably can't help the model much, then consider deleting that feature from the model inputs and seeing how much quality is lost by its removal. If the model works just or almost as well without it, that's great. Conversely, if you don't have enough complete examples to train a useful model, then you might consider imputing missing values. Imputing missing values is guessing, seeing other values and guessing what this value could be. That's imputing the missing values. If I have sufficient examples, then I could just delete this particular uh, data, that missing data. It's fine to delete useful or useless or redundant examples, but it's bad to delete important examples. Unfortunately, it can be difficult to differentiate between useless and useful examples. If you can't deduce whether to delete or impute, consider building two data sets, one formed by deleting incomplete examples and other by imputing. Then determine which data set trains the better model. That's better. One common algorithm is to use the mean or median of the imputed value. Consequently, when you represent a numerical feature with z scores, then the imputed value is typically 0 because 0 is generally mean z score. By times type. Is 23 would be. Coming to labels. Direct versus proxy labels. Direct labels identical to the prediction of the model you are trying to make. That is, the prediction your model is trying to make is exactly present as a column in a data set. Okay, that is direct labels. If I had a target the model was supposed to predict and it was already available in the dataset, that is known as direct labels. For example, a column named bicycle owner would be a direct label for a binary classification model that predicts whether or not the person owns a bicycle. Proxy labels, which are labels that are similar but not identical. That is, the labels are similar but it doesn't exactly have that particular label in the dataset. A person subscribing to Bicycle Bazaar magazine probably but not definitely owns a bicycle. Direct labels are generally better than proxy labels. If a data set provides a plausible direct label, you should probably use it. Oftentimes, through direct labels aren't available. Proxy labels are always a compromise. Okay, if you don't have direct labels, you use proxy labels. That just not a big deal. Recall that every label must be represented as a floating point number similar to the feature vector. Sometimes a data label exists but can't be easily represented as a floating point number. In this case, use a proxy label. Your company wants to do the following: mail coupons get to bicycle owners. So a model must do the following: predict which people own a bicycle. Unfortunately, the dataset contain a column doesn't contain a column in bike owner. However, it does contain a column in recently bought a bicycle. Would be a good proxy label. Okay. Then human generated data. Some data is human generated. That is, one or more humans examine some information and provide a value, usually for the label. Okay. For example, one or more meteorologists could examine pictures of the sky and identify cloud types. Alternately, some data is automatically generated, determines the value. For example, a machine learning model could examine sky pictures and automatically identify cloud type. Explores the advantages and disadvantages of human generated data. Human generated data when perform a wide sophisticated, the processor forces the owner of the dataset to develop clear and consistent criteria. There are human errors and there are errors humans and they are expensive. Think through this question to determine your needs. How skilled must your editors be? Must you know a specific and do you need linguists for dialogue or NLP? How many labeled examples do you need? How soon do you need them? What's your budget? Okay. For example, label 100 examples. Imbalanced data set. Coming to imbalanced data set. This section explores the following three questions. What's the difference between class balanced datasets and class imbalanced dataset? Why is training an imbalanced dataset difficult? How can you overcome the problems of training imbalanced datasets? Okay. Consider a dataset containing a categorical label whose value is either the positive class or negative class. Okay. In a class balanced dataset, the number of positive classes and negative classes is about to be equal. For example, a dataset containing 20 boys and 20 girls. That's good. So we have 235 positive classes and 245 negative classes in a balanced dataset. In a class imbalanced dataset, we have the ulta. When less than 0.1% of the examples, okay, the more common label is called the majority class and the more less common is called minority class. The difficulty of training severely class imbalanced dataset. Training aims to create a model successfully that distinguishes the positive class from the negative class. To do so, badges need a sufficient number of both positive classes and negative classes. That's not a problem when training on a mildly class imbalanced dataset, since even small batches typically contain sufficient examples of both the positive classes and negative classes. However, a severely class imbalance might not contain enough minority classes, for examples, for proper training. If the batch size, most batches won't contain any examples of the. Okay. Training and class imbalance dataset. What each class look like, that is, what feature values corresponds to what classes, how many each class is, that is, what is the feature which you marking. Downsampling, dividing the original data set, transforming data. I think this is just theory, man. We can just skip all of this. I think I know all of this. L2 regularization, model complexity, overfitting, generalization. We just go with neural networks embeddings next time. Good afternoon, Ankit, Karan, Jakar. This is too much theory, man. Like, it's a lot of theory. We should be fast enough to end this, okay? Probably I will do it at afternoon, a stream again. Probably, I don't know. Probably from 6 to 8. Uh, yeah. Okay, yeah. And that's enough, man. This is all theory. This is too much theory. We have to finish this probably today, I guess. I'll do one thing, I will complete this today and explain to you guys, give you a summary, like fast as fuck, and we can stop, okay? And we can jump directly to projects. Okay, then thank you all. Love you. Bye.